Hello and welcome everyone. In this video we are going to extend our knowledge over the topic logistic regression. In our previous video we have seen about the hypothesis function, about the cost function, and in this video we will learn two strategies to solve the multi-class classification. So if you remember, we so in our last video we had talked about only of 0 and 1 and accordingly made our cost function that way. So if you notice, there are only two classes. But today we will learn how to solve a logistic regression problem with more than two classes basically. So we will call that multi-class classification, and we would also solve overfitting issues with some regularization concept. So we'll understand that one by one. So about this multi-class classification, so instead of 0 and 1, let us have three colors as our classes: red, blue and green. So there are two approaches. One is one versus rest method, and another is one versus one method. So we can take, first I am discussing about this one versus rest method. We have red, blue, green. So our binary classification problem 1 would look like red versus blue, blue comma green. It means red versus not red. Okay. So basically what we would do is, let's say red signifies 1 and not red signifies 0. So this is our binary classification problem 1. Similarly, we will do blue versus not blue. So here blue will signify 1 and not blue will signify 0. And in this way, no matter how many classes we have, suppose we have n classes, so we have to make n binary classification problems. So this is the method of one versus rest. So you can understand this easily. Let's say one versus rest gives some values, classifications as cat, cat and not cat, let's say, and this model 1 gives us the probability of y being a cat. Similarly, model 2 would give us a probability of y being a dog, and similarly model 3 would give us a probability of y being a rat, and henceforth this is an extension of, you can say, or somewhat similar with the Bayes theorem that you may have learned earlier, or you would also find in the mathematics for machine learning video. So actual probability can be calculated by probability that y equals to cat is divided by sum of all the probabilities of all the classes. So in this way we would solve a problem of 1 versus rest. 1 versus 1. In 1 versus 1 we will take one color and then one by one compare it with all others. So red versus blue, red versus green, this is a binary classification. So you can see we require many classes. So basically which one would be more time consuming? 1 versus 1, because we are classifying here. To classify here we need actually 6 different problems, and earlier we needed only 3. So you can see here the formula for calculating number of models is num classes multiplied by num classes minus 1. So actually here red, blue, green and yellow is also there. So red, blue, green, yellow would take us to 4 classes with 1 versus rest, but with 1 versus 1 it would take us to 3 classes, 3 problems. And so the number of problems, 6 problems basically. So the number of problems can also be calculated from here. 4 into 3 by 2, so it will be 6. So 6 problems we require, and 1 versus rest we require only 4 problems. So now there is something called an overfitting problem. So it is a modeling error which occurs when a function is too closely fit to a limited set of data points. I had clearly explained this in linear regression also. So what happens in here logistic regression, I told you that this hypothesis function, and it takes arguments as m1 x1 m2 x2. So here they are represented as theta 1 x1, theta 2 x2, and the theta naught x naught, you can say, where x naught is equal to 1, you can represent it that way. Basically it is the product of two matrix, one is transpose and one is normal. So you can understand this from clearly understand this from our previous video. So now a bit more adding higher degree to our function will reflect in being a more particular decision boundary. Now what will happen if we add all the 3-degree features, 4-degree features and all the n-degree features also? So it will overfit, it will be very particular in separating the classes, and it would also perform a very high accuracy on the training data, but our testing data will fail drastically. So this is the overfitting problem. So we basically regularize this overfitting using something known as L1 and L2 regularization. So one way of reducing overfitting is by regularization. A simple explanation of regularization can be it discourages complex features in the data set. Let us try to understand this. So we had m1 x1 plus m2 x2 as our classes. So we add all the 2-degree features also. So this concept arises from the polynomial regression. I had explained you this, how it leads to overfitting. Now our input to the sigmoid in case of logistic regression, we are adding this term to the cost function also. So why we are adding this term? If you notice here, these are the 2-degree curves squared, and this is the regularization parameter. Beta is known as the regularization parameter. And so if you increase beta, what would happen? You try to think on your own, what would happen if you increase beta, and what would happen if beta is too low? If beta is too low, it would mean that the regularization is not much important, and if beta is too high, we are giving special stress on the regularization. So that would lead to basically underfitting. So we will understand this. So L2 regularization, so what is the essence of this? Basically we saw that our cost function would be something like the minus log of and all the summation of all the data points plus 1 minus y into minus log of 1 minus y. Those concepts I have explained in the previous video. So that is our error function. We multiply some constant c with that and plus lambda into this regularization parameter, regularization term. So if you imagine for a large value of c, the regularization term would not be important and hence would lead to overfitting. If the c value is very large or compared to the lambda value, then we are saying this term is not much important to me. I would neglect this term, and this would lead to overfitting. And now what if c value is very less and lambda value is very high? So I am telling that I am not caring much about the error function to our cost. I am only caring about the regularization. So this will lead to underfitting. Can you understand this? For a large value of c, we are giving much stress to our error function. The regularization term may not be important and would lead to overfitting. So a change in this regularization term would not be as important as a change in the error. So I would like to minimize my error to minimize the cost function in case of a large C, and hence it would lead to overfitting. So a very balanced C and lambda values are very necessary. So similarly, so this is the L2 regularization, and similarly there we have another term called L1 regularization, where instead of sum of squares we use the sum of the modulus values of the coefficients, and this is our error function as a function of x and y. This was clearly explained how is this coming in our previous video. So basically e as a function of x is this thing. So yeah, that's all from this video. In the next video we will see something more about these topics, and then we would also work on some projects in probably in the next video. Till then, thanks a lot.